record now?
Yes, I can.
Okay, good. All right, let me get MATLAB up. People. All right, what do we got? 19 people are coming online. All right, got 20. We normally have 26 to 27, I think. By the way, you're posting these on YouTube, aren't you?
Yes, sir. So far, all the recordings up to this point have been posted, except for I think like the first or second.
Okay, that's all right. All right, so I guess we'll open up with, are there any questions first?
Could you do number 1B part 3? I believe I did the multiplying together correctly, but I was struggling with how to do the partial fraction expansion of it.
Hold on, let me find it. This is homework 23, you said, right?
Yeah, homework 23 part 1.
Which one?
So the first problem B, and then the triple I. It was convolving 3/4 to the n u of n by 1/2 n to the u of times u of n.
It's not convolving.
Well,
it's just
evaluating. Well, yeah, evaluating y of
Let me
n.
cast the screen. And by the way, I've got a document cam I'm going to be using in a second. It'll make it a lot better, I think. Let me first share the screen, make sure everybody sees it. That should be the one shared, I think. Can you all see? This is due Friday, A and B. Can everybody see that?
Yes.
Hey, by the way, if you're having trouble uploading the homework because you didn't say a homework 23, I think Ruth sent me a message on that. I will deal with that right after this lecture, all right? I'm going to let you put it in basically any time today. I just want to get on record some stuff in there that I can print out and grade accordingly. Okay, so you're asking about 3 right here?
Yeah.
Well, that's not doing any convolution. It says if this right here, you're evaluating this y value here, right? You see that this is x of n, correct?
Oh,
This
yeah.
this is x of n. Well, if it's x of n, let me try to do this on a doc cam. This is great, this thing, if I can get it. All right. I'm just going to push it down here. And this is really nice. This is a good doc cam. I can rotate this any way I want. Now, can you all see that screen okay?
Yes. Yes.
Everybody?
Yeah, we can see it.
All right, so they have, first of all, the was what? Y of n minus y of n minus 1. And what was the other part of it? I just had it up.
Is equal to x of n?
Is that it?
Yes.
All right. Here, we just do the z transform. I mean, sorry.
Hold on, Dr.
There's a
Bedinsky.
1/2 in front of that
Yeah.
y and minus 1.
Yeah.
1/2?
Yeah.
Everybody okay with that?
Yes.
All right, now if we take the DTFT, so now I'm going to take DTFT of this, then I get y of omega. I'm not going to put the e to the j omega. It's a function of omega, okay? And then I have that times 1 minus 1/2 here, right? But there's that -1 operator right there. So what does that do? It brings out a e to the minus j omega, correct?
Mhm.
And that's equal to x of omega. Whoever asked this question, I want to make sure you can see. Can you all see this here?
Yeah.
Yep.
All right. Now, if that's the case, the next thing I'm going to do is simply find out my transfer function, h of omega. I'm going to do that, which is y of omega over x of omega. This is the thing you always want. This will give you your impulse response. And that is simply just 1 over 1 minus 1/2, right? Times e to the minus j omega, correct?
Yes.
That's a lousy omega. Everybody see that?
Yes.
Yep.
Okay, now that I have that, I can tell you right off the bat what h of n is. That's the inverse transform of that. And that's going to be simply 1/2, right, to the n u of n, correct?
Yes.
I'm
Yep.
going through, I'm really analyzing the system in its entirety. Now, if you want to know for a specific input what it is, for x of n equal to, what was it again, somebody? 1/4 or 3/4, right?
3/4
To the n
to
u
the
of n.
n u of n.
All right, now you can do this if you want to convolve this right here with the actual, sorry, if you take this as x of n and you would solve a difference equation to get y of n, but you don't need to do that. It wouldn't even be a convolution in the true sense. You could convolve it with h of n. You could convolve this with this, or you could simply take this x of n, stick it in here into the fundamental equation, and just start at 1 and count. If the initial conditions are 0 and y of n, you would basically say that y of n for n equals 0, right? N equals 0, this right here would be simply 1, correct? X of 0 would be 1. You would put it in here, you have 1 equals, well, y to the n minus 1, or y to the minus 1 is 0, is equal to y of n. So y, the first value is 1. Then you increment n equals, n equals 0 there, then n equal 1, then you would get 3/4 here, you plug it in there, you find the new value for y of 1 equal to x of n plus 1/2 y of n minus 1, which is 1. You follow me on this?
Yeah.
That's the way to do it if you want to do it with a difference equation, and you can write a simple for loop in MATLAB to do that. However, if you want to do it the smart way, in my opinion, by just doing the transform of this and then multiplying them. So what I'm going to do is say that now my y of omega is equal to x of omega times h of omega. This is where I'm going with this, right? Okay, what is that going to be? Well, that's equal to 1 over 1 minus 1/2 e to the minus j omega. That's my h of omega, right? And then what's the transform of this one? Isn't that just 1 over 1 minus 3/4 e to the minus j omega, class? Everybody?
Yep.
Yes.
Yeah.
So you multiply that. Okay. And now you see you have 2 poles. That's one pole. That's another. You do a partial fraction expansion. Do you want me to do it?
Yeah, so I
Okay.
got to that point. I was struggling with what to do, like the actual partial fraction expansion with this.
Let me show you a simple way to do it.
Yeah.
And
That was the same for me as well.
let z here, all right, be equal to simply I almost feel like showing you how to do this with z transforms. If you're going to do this with a partial fraction, here's what it amounts to is you could take 1 over 1 minus 1/2 e to the minus j omega here times 1 minus 3/4 e to the minus j omega. And you're going to have a over 1 minus 1/2 e to the minus j omega plus b over 1/2 or 1 minus 3/4 e to the minus j omega as before, right? Correct?
Yep.
Correct.
Now, what we want to do is find out and understand this. I'm going to find a. So I multiply everything by that, right? And you know what I'm going to have here. I'll have 1 minus 1/2 e to the minus j omega, right? Then it gets rid of that, correct?
Yes.
Now, you simply say, I want this to be a pole at that point. So that means 1 is equal to 1/2 e to the minus j omega. With me?
Yep.
Y'all
Right.
see that would be the pole. That's where this part right here would go to infinity. So that means I have 2. There's an easier way to do this that I'll show you in a second with z transforms. That's why we're going to do z in a second. I'm going to have 2 is equal to e to the minus j omega. Then I take the log of both sides, right? Then I get the natural log of 2 is equal to minus j omega, correct?
Yeah.
And that means omega, take 1 over j, multiply by minus and then divide by j. So you have j down here and 1 over j is just going to be equal to plus j. You end up with plus j here. So omega for the first pole is at this value. Do you understand that?
Yeah, and that's j natural log of 2 is equal to omega.
Yes. And now you take that value of omega and you evaluate this with it to get the value of a. Now it's complex. Do you understand that?
Yeah.
All right. So, or it's likely to be complex. And B will be likewise, it'll be complex. But when I get to Z transforms, and we're going there, this will be very easy to do.
Okay.
Dr. Bakinski.
Yeah.
So for that question in particular, we're looking for when 1 minus 1/2 e to the j omega
Goes to infinity.
or goes to infinity or goes to 0.
Well, the downstairs part goes to 0, right? That means 1 has to be equal to 1/2 e to the minus j omega, correct?
Right.
And that's
So
what this is right there.
so would that be the same as equating e to the negative j omega
You
to
can
2?
just do it this way. Yes, you can just use that. Exactly. I'm showing you the value of omega that causes it. You can just say e to the minus j omega is 2 and plug it in right here. And then you can get it. And that's much.
And can
that's
you
not
also,
complex.
you also plug that into the 1 minus 3/4 j omega, not, right?
Well,
Because it's the same,
let-
e to the j omega is the same for both of them.
when we got the pole, right, we said the pole was e to the minus j omega was equal to 2, correct?
Yes.
That's
I have to scroll down a little bit.
I'm sorry. Y'all with me on that? That's
Yes.
what we agreed the pole was. Now, what was left inside? We still had 1 over 1 minus 3/4 e to the minus j omega was equal to some a, correct?
Yes.
All right, now we plug in 2 here. So we have 1 over 1 minus 3/4. I said complex. It's not complex in this one. Times
Yeah.
2 right here. Instead of getting omega, we can literally plug in e to the minus j omega. You follow me?
Yes, sir. I was like, that's exactly what I did. I thought that
That's the way to do it. And then
yeah,
that becomes just 1 over 1 minus what? 3/2, right?
yes.
And that's 1 over, basically this is this is 2/2 minus 3/2 is minus 1/2. So it'd be minus 2.
Right. Okay. I heard you say complex and I was like, I definitely didn't get
I'm
that.
sorry. It can be complex. I'm sorry. It can't be in a real and imaginary. But you can either solve for omega or you can solve for e to the minus j omega. And since you're going to be plugging in e to the minus j omega, it makes sense just to solve for that.
Yeah.
Everybody?
Yep.
You get it?
Yeah, that makes sense.
All right. But it's really it's a simple partial fraction expansion. That's all that is. You're not used to thinking of expanding with this kind of a term, though. That's the problem. Okay.
Dr. Baginski, I had a question. I don't know if you had answered it prior to me joining the meeting or not, about turning in the homework.
Well, you're going to have till 5 o'clock today. I apparently didn't put a homework 23 thing in Canvas, right?
Right.
Right.
Yeah, I was just wondering how, like, if you were going to post that today or whatever for us
How
to
about
turn.
I do this? All right. So for the sake of everybody, I'll put in a specific link, homework 23. All right. and I'll make sure that it's just for this one. We all put it in there. Now, what they do, I found this out the hard way. I can't download that thing quick. What they do is take it and they turn it into either a RAR or a zip file, and then they send it to me. And it takes some time for them to do that. And so it's not like I can just, well, I'll grade homework right now. It's not that simple. It may take an hour, it may take 2 hours before I get the homework. I learned that lesson this morning when I tried. Now, my other class, what I did is create individual drop boxes for everybody because they're smaller numbers. And I gave the student the right to put anything in their Dropbox and edit it in myself, but nobody could see anybody else's Dropbox. And I had, I think, 7 or 8 people in that class. And it's much easier doing it that way, I'll tell you. Because Canvas is slow to get me information because so many people are on it right now. Fair enough?
Okay. Yes, thank you.
All right. Now, something else that I think you guys are going to remind me of is test date, right?
Yes.
Yes, sir.
All right. Can you give me some feedback, Lydia? When did anybody get back to you on when they want it?
We haven't really had a poll or anything.
How about we do this? Why don't we do this while in the discussion right now? You guys can get on GroupMe simultaneously, I assume.
I can make a poll for it really quick.
Yeah, and just find out, make it for the next, like, say we got Monday. I don't know if we have any days off coming up. We got Monday, Wednesday, and Friday, and then the next Monday. How about we make it in those 4 days? Next Monday, next Wednesday, next Friday, or the following Monday. And to me, it doesn't matter. What I'm going to do is this. I'm going to probably the way I've been thinking about this, email you a test, all right? And then what I'm going to ask you to do within a 2-hour period, I'm going to give you a full 2 hours on this one. Send it back to me. I have to have it within 2 hours. I may do it on Canvas, depending on how Canvas works. If not, I'll just have it send it directly to my email. And then, but that's more of a problem for me sorting through because I get, and don't send me anything with Gmail, please. Some of you are sending me Gmail questions. Auburn University considers a lot of that phishing attempts, and they put these labels on it, basically warning me not to open it. And so send me through the Auburn email, and also put right in the title, like test, something where I know for a fact that it's the exam or exam 1, that's your exam, okay?
Okay, the poll is up, so
okay.
let's see.
Well, just tell me what results, and I'm trying to work around everybody else who's giving exams. That's that question. I hope I answered it. Let me do one other thing here. Now, this document camera is going to be great. Do you have other questions, by the way?
I had one more question about the homework.
Okay.
Okay. It's gonna be the.
Hold on. Let me get it. Go ahead.
The second A and B part. It doesn't clearly have a number, but it's the second A and B.
All right. The cosine?
Yes.
All right. Why don't we do, great question. Great question. So what I'm going to do is pull this over here so I can see it. And then bring up my window. I hope I get better at this as time goes by. So for the second homework, it starts with they have h of n equal to, I don't know why, it's not darker, h of n equal to 1/2 to the n times cosine of pi over 2n, right, times u of n. Now, what I'm going to do is this. Since we're going to be talking about the property of that makes this so beneficial, I'm going to say it again. If this is h of n, I know also I have an h of capital omega that is simply the inverse transform of, or is the actual DTFT of that, right? We'll do that in a second. Do y'all agree?
Mm-hmm.
Yes.
I could. My window, I can't see most of you. I don't know how many people are on video cameras. I got at least 3 that I can see, but I don't know if anybody else has a camera. Oh, Ruth, you have something. You have a visual ID of some sort. A screen saver, something like this. Anyway, if you have cameras, you can go ahead and turn them on and see if they work. And see if this starts to be a data intense thing where we start getting people dropping out, then what I'll do is ask you to shut off your cameras. But until that point, it's easy for me to see if you understand if I can see you. But if I can't see you, I don't know if I'm talking to dead air. All right, so this is going to be the transform of that we'll do in a second. Do you agree?
Yes, sir.
We've got the x of n, and that's equal to cosine of pi over 2n, right? Correct?
Yes.
Now we could get y of n, which would be x of n convolved with h of n. We could do it that way, correct?
Oh, yeah, that's probably easier too.
I don't know about that. I wouldn't do it that way. Here's what I would do. I would go ahead and take the transform of that. Well, first, remember what the transform is of this. Isn't that just it's a doubly infinite? It's a series that starts at minus infinity, goes to infinity. But in your book, they have the transform of cosine of pi over 2n, correct? We can do it if you want, but what is it? Take a look. Isn't that just what? It's pi over 2, right? Times what? Think of it this way. Here's an easy way to do it. All right. What is the transform of 1? If this is in the n domain and this is in the capital omega. Come on, guys. We use duality, right? What happens? It's 2 pi times what? Delta of omega, right? But we have to do one thing. This thing should repeat itself every 2 pi. Now, I'm not going to add that now, but you all know how it's step and repeats all up and down the axis. So normally the way they write this, it would be 2 pi, and then they would have a sum of delta of capital omega minus 2 pi n, and they would have n going from minus infinity to infinity, just to make sure it's step and repeats. That would be mathematically rigorous. In engineering, generally, we don't even need that if we need a specific answer. Everybody okay with that? Mm-hmm. We don't have to do step and repeats. So if I have that as such, when I look at this cosine of omega, I know that what? X of n times cosine of omega naught n in the book is what? That's equal to 1/2, right? X of omega plus omega naught plus X of omega minus omega naught. Correct, class?
Mhm.
Yes.
Everybody?
Yes.
Where is this in the book?
Modulation is one of the properties I put down explicitly. You can get it because the book, I think the book has this one. I've got to reach my book, hang on. Hey, can somebody tell me what page that is on that transform? Or that operation? It's on, should be on 3, oh, that Z transform, sorry. Oh, this one, it's straightforward. It's on page 398. They actually have just the cosine itself. But the cosine modulation is one that I did and made sure that I emphasized the fact you should include it. Do you all remember that class?
Yes.
The one thing I would do
Yeah.
right here in your books, if you have them, I would, let me just do this. I'm trying out all these features, the magnifier now. Try to get a low glare angle at this. Right here in your book, I would just put down the modulation with cosine and with sine. And by the way, they have the straight cosine transform right there. And you see how they always have that plus or minus, or that minus 2 pi k, because its extent is infinite.
Mm-hmm.
Okay, follow me on what goes next. All right, I'm doing it this way though for a reason, because you're going to have cosine and sine multiplying a lot of different functions, not just a simple delta function. So we know we really have one multiplying the cosine, right? So the only thing we do is we say 1 times cosine of omega naught n is really going to be this. It's going to be 1/2 times the actual transform. That's this. That's the transform of x of n between minus pi and pi. Only it will be a delta of omega plus omega naught plus delta of omega minus omega naught, correct? And there's also the 2 pi. So when everything's said and done, you get this. And this is in the book, cosine of omega naught n simply goes to, the transform of that is simply pi times delta of omega plus omega naught. It's the same as the actual continuous time Fourier transform, plus delta of omega minus omega naught. Everybody agree with that? Making sure you all see it. If I'm talking a little fast, it's because I want to get to something besides this. But you okay with this? Everybody?
Yes, sir.
Anybody have
Yes.
any more questions about what we've done so far? So I have the transform of this. What's the transform of this right here? I'm going to zoom out a little bit.
That's in our book as well.
What is it?
Is e to the j2 omega minus 1/2 e to the j omega times cosine of, in this case, it would be pi over 2.
For 1 second. Oh, they do have that.
Yeah, it's number 8 in the
Yeah.
that same table.
Well,
I used modulation instead of that
It's
transfer table.
I think it'll work with modulation just as easy. We can. So if we have, first we know that if we have a to the n u of n, that simply goes as 1 over 1 minus e to the, e to the minus j omega, correct?
Right.
And if you look at that as your x of n, that's being multiplied by cosine. So if this becomes this x of n, can everybody follow me?
Mhm.
The only thing I have to do is take this function, divide it by 2, and then spread the omega on either side. And I'm about to do that on the next page, okay? With me?
Mhm.
Remember, this is what? That is my x of omega. So now I have to take this x of omega, and I have to replace the argument of omega with omega plus omega naught and omega minus omega naught, right?
Mhm.
All right, I'm going to do that in the next page. Here, I'm going to go ahead and say that I'm going to have the transform of, and I'll just do a to the n cosine of omega naught n by itself. This will be equal to 1/2, and then I'm going to take the transform of a to the n u of n. There's a u of n here by itself. So it's 1 over 1 minus e to the minus j quantity omega minus omega naught, right? Plus 1 over 1 minus e to the minus j omega plus omega naught. And that is the actual transform of it, correct?
Mhm.
Don't forget the A in front of the E's, I think.
Yeah, you're right. You're absolutely right. And what does it want now? Okay. Once we have that, how do we actually get the value of the response? What do we do? Well, there's a lot of things we can do, but why don't we just do it by brute force? Let's just take a look at this right here and find out what the inverse is, okay? So in the frequency domain, I have really 1 over 1 minus a, right? And now I factor out that e to the minus j omega naught, which would be plus j omega naught there, correct?
Mhm.
That's like one constant. And then I have it times e to the minus j omega. I didn't put the half, I simply looked at this by itself. Does everybody follow me?
Mhm.
Yes.
Give me a thumbs up kind of deal. Try to get you guys to see how many. I got 1, 2 and a half. Okay. All right, now this that I'm circling right there, that boxing I should say, that is, sorry, let me get rid of that. That right here I'm trying to sharpen that up a little. You can see that, right?
Yes.
That's like a
Yes.
constant. I'll just call that b. So I know that 1 over 1 minus b e to the minus j omega is really just going to be b to the n u of n, correct?
Yes.
Right.
Okay. Now, what is my b? My b is this. So I go ahead and I say, this is really, when I look at this transform pair, to go back the other way, well, to tell you the truth, I'm sorry, I have to take this and, wait a second. Hold it, I don't have to do that. This is this right here, and I gotta pull this over here for a second. This is my h of omega that I have. I'm sorry. Do you follow me on that? My h of omega is this right here that I put down where my pen tip is, right here. So this is my h of omega. Now I have to take that and multiply it by the cosine. Let me just do this pictorially, and I'll try to make it clear to you. Here, if this is the omega axis, and we call that pi, that minus pi, and then we take a look at just the h of omega, what does that look like? Well, it looks like at that frequency minus omega naught and that frequency plus omega naught, we basically have this type of a waveform. If we talk about the magnitude of h of omega, it does this. Can you all follow me on that? Just a rough sketch. That would be what the magnitude of h of omega looks like. Everybody agree with that?
Yes.
Yeah.
Okay. Forget about the magnitude right here. We can get that value by just inserting the value of omega naught here and here, and we can extract it, but that's not important right now. Now, what happens when we take the transform of the cosine of, and I'm calling that omega naught, let's call this omega 1 n. Well, that's going to be what? Just pi times delta of omega plus omega 1 plus delta of omega minus omega 1, right? Correct?
Mhm.
Okay.
Now, what does that look like? Well, wherever omega 1 is, suppose it's there, and suppose it's here. That would be minus. Then the only thing you're going to do is extract the value right there of those 2 points. You're going to basically evaluate this filter at this function and at this value plus omega 1 and at minus omega 1, right?
Yep.
And then you're going to multiply it by a delta function because that's the only output that happens. So let me do this for you. Here is my function h of omega. So the way I get my final result is this. I take h of omega and I let omega be equal to omega 1. That's this frequency of the cosine. I take that and I multiply it by delta of omega plus omega 1. Actually, this is going to be minus omega 1 right there. So it'd be minus omega 1 plus h of omega equals plus omega 1. And it would be delta of omega minus omega 1. And that would now be your frequency response. This would be y of omega. Does everybody follow me on that? And I've got a point.
A little bit, not super clearly.
Let me go ahead and do it this way. Stay with me now. Just stay with me. if I take a look at magnitude of h of omega, right? And I'm just drawing this. I know we had some omega naught minus omega naught plus omega naught, right? And I said that that's where these things would peak at, because that's the cosine frequency that's multiplying that a to the n and the filter response, right?
Yes.
All right, now that's a filter response. What are you really doing there? You're saying that if, in fact, I have a frequency right here at, say, omega 1, and here at minus omega 1, a single frequency, a cosine waveform, that filter simply is attenuating the magnitude of the delta function, or it's weighing it by its value, h of omega, at that frequency. So my y of omega, my output, is simply going to be, I'll start down here, it's going to be h of omega equals minus omega naught, omega 1, times a delta function of omega plus omega naught. That means, or omega 1, pardon me. That delta function has to be there, because this, remember, there's only, the whole idea is the input is a continuous frequency. So what we have to do is evaluate the filter response at just two frequencies, the plus and minus value of the cosine waveform. Okay, got it? Remember, the cosine, that's our x of n, was equal to cosine of omega naught n, right? And that translates at two distinct frequencies, only two distinct frequencies by delta functions. It's pi and it's delta of omega minus or plus omega naught, right? And it's
Yes.
plus delta of omega minus omega naught. Go ahead.
I'm just confused when you have your h of like omega is equal to negative omega 1. Where does the pi go?
It doesn't go, it stays there. But remember, it's, I should put it right there.
Okay, all
It
right.
doesn't go away. It's now, pi would be there, and it would be h of omega equals omega 1 plus omega 1 times delta of omega minus omega 1. And that would be, you all see what we really got here, though. What is it? It's just taking the delta function and it's weighing it by the magnitude of h evaluated at those frequencies. And if you think that's exactly what a filter does, if you want to know the output of a filter and you have a frequency response, right? You got the actual transfer function. You just find the frequency of the input and look at the magnitude of the filter. Whatever that magnitude of the filter is, then you multiply the input by that and you have the output. It's still at the same frequency, right?
So this is the magnitude of the output?
No. I had to show with magnitude because I can't show a complex value of h. There's magnitude and phase, all right? But what I'm going to tell you is h of omega here is complex in general. Are you with me?
Okay. Yeah, I think so.
Now I'm going to show you a trick that you're going to like. Now, what does this actually look like? It's just two delta functions. What the actual output y of omega looks like, it would be at minus omega 1 right here and plus omega 1. And it would just be a delta function like that, with the height being pi times the value of h of omega 1. And this would be pi times h of minus omega 1. Now, what does that translate back in the time domain as? Here's what is a beautiful thing. The only thing you get is this. You're going to take the magnitude, your actual y of n will be equal to simply the magnitude, please get this down, the magnitude of the transfer function evaluated at omega 1. It'll be symmetric. That's the frequency of the cosine. Times the cosine of omega 1n, that's the original function, right? It's cosine of omega 1n, correct? And then you have to add the phase to it. So you add the phase of h of omega 1. And that's all there is to this. So putting in perspective and doing the exact problem, if I have an x of n here equal to cosine, what was the was it pi over 2?
Yep.
Right? And this is the exact problem, right?
Yes.
So do you evaluate it at negative pi over 2 and positive pi over 2?
Just positive, just positive.
Just
If you take a
positive.
look at the inverse transform here, it'll, the 1/2 that we broke this out and stuff like this, it'll cause them to fuse back together. But let me just show
Okay.
you right here what happens, okay? My x of n is cosine of pi n. It goes in to a filter that has a transform h of omega. It doesn't matter what that transform is. All right? It wouldn't matter what we had here. If we had a functional form, an explicit mathematical functional form here, that's the only thing we need. My output y of n here will be simply equal to the magnitude of this function here. So it's magnitude of h evaluated at pi over 2, because that's where we have to do it. And then it's going to be times, well, the multiplier here in front of the cosine is 1, so it's just 1 times the cosine series would retain itself. Then you would have the pi over 2n, but then there would be a possible phase of h of pi over 2. All right? With me? Now let's evaluate h of pi over 2. I got to go back one page. So go back here, and where was it? I have to go back another page. No. So basically, h of omega equals what? Remember? That
H
was
of
1/2 times what? 1 over 1 minus, right? And the value of a was 3/4, right? Isn't that right? Am I wrong?
For this one, I believe it was 1/2.
All
It
right.
is 1/2.
Sorry.
Yes.
This would be 1/2. And then it's e to the minus j. And we have omega minus, what was the thing multiplying the first one? Was a cosine of what in the first one? Pi over 2. It is pi over 2. Oh, beautiful. So this is pi over 2, right?
So that means there's not going to be another phase angle.
Well, I don't know yet. I'm not sure. Minus 1/2 e to the minus j. And this would be omega. Actually, that would be plus. This would be minus pi over 2, right? That's the h of omega, right?
Yeah.
Everybody?
Right.
Now we evaluate it at omega is equal to pi over 2, just one time. So when it's pi over 2, what do you see happening here? Well, this goes to simply e to the 0 or 1, right?
Mm-hmm.
Right.
And what does this one go to? Let me write it down. This is going to go to this whole h of pi over 2. It simply goes to what? 1/2
Negative.
times, and then this one
Doesn't
will
that
go to
whole thing turn
pi,
into -1?
Yeah.
right? It goes
1
to
over.
1 plus 1/2, right? Plus 1 over 1 minus 1/2, correct?
Mm-hmm.
Yeah.
Right? And you can see what? This, that's 3/2 inverted is 2/3. So my filter response is going to be that. And this would be 2/3 plus, and this is simply 2. Correct?
Yes.
Then you can see what happens is really what we're going to have is 1/3 plus 1, or this is 4/3, right? Agreed?
Yes.
Yep.
Well, 4/3 has got a phase angle of 0 degrees. So your output, after all this discussion, the output is simply going to be equal to, and I'll put it right here, y of n. Maybe it's just going to be that, which is 4/3 times cosine of this, which is pi over 2n, and the phase angle is 0. And that's the output. That's what you get. And this is the neat thing about sines or cosine inputs to a system. And let me underscore this. But did you have a question?
I did have a quick question. Can you explain one more time for the first part how you got the 1 over 1 plus 1/2?
Yeah. You see here we had 1 over 1 minus, and this is what? 1/2
1/2.
e to the minus j omega plus pi over 2, right?
Right.
All right. Well, when omega is pi over 2, this would be pi over 2 plus pi over 2 is pi, right?
Correct.
E to the minus j pi is what? That's 1 at an angle of minus 180 degrees is minus 1, isn't it?
Right.
Minus 1 times minus 1/2 is plus 1/2, right?
Okay.
So that would be, this would be 1 over 1 plus 1/2. The other is 1 over 1 minus 1/2.
Okay. That makes sense. Thank you.
All right. Now, in general, I want to just say this. Doesn't matter if the waveform's a sine or a cosine, but if you have x of n into a system, and it's equal to some constant a, I'm going to use a cosine of omega naught n plus some phase angle. And you put this into a system. And the system can be defined by either h of n or by h of capital omega. It doesn't matter. It's a filter property. Your output here will be at this frequency. It will only have that frequency component. Do you understand that? For a linear time invariant system, it will only have omega naught. Think of your circuits courses. Remember, when you were doing circuit analysis at a constant frequency, you turned everything to a phasor, right?
Right.
All right, what did you do? You suppressed the j omega. You basically suppressed the cosine of omega t plus any phase angle. You turned it into magnitude at angle, right?
Right.
Well, the only thing you care about now here, if you do it in the phasor domain or in the frequency domain, when you transform this, you get a magnitude and an angle. You don't, and it's going to be centered at omega naught. Here, you have a frequency response. These two multiplied together, because this is delta functions, will only extract the value of that filter at plus or minus omega naught. And the real thing I'm telling you is, the only thing you need to really appreciate about this is your output will be the A, and it will be times the magnitude of this filter, take the transform of H, evaluated at omega naught, then use the same cosine of omega naught times n plus the original phase angle, and then plus the phase angle associated with h of omega. And you got it. And that's it. Okay?
Okay.
You got me on this one? This was, I was going to do this.
In your lecture from last spring, you went over this problem, but you did it a little bit differently. You changed the cosine into Euler's
You can do it
equivalent.
that way too.
And so I guess my question is like, so for that, you did the same kind of transfer function, but it was when you have a like E function going into an H of omega. Is that like hold for almost any function if it's a constant frequency going into
As long as it's an infinite series constant frequency. If I went and put in here, instead of this, if I put in x of n is equal to a e to the j omega naught n, right? If that was what's going in, then my output coming out would be the same a e to the j, and there'd be quantity omega naught n plus phase angle of the filter, all right?
Okay.
And it would
And then
also
would
be
you-
times the magnitude of h of omega naught. So it's going to be multiplied by the magnitude, and the phase angle would be added into that argument.
Okay, that makes sense. Thank you.
Yeah, but the real thing is these are constant frequencies. You could have a cosine of omega naught n. You could have a sine of omega naught n plus a phase angle. You could have an e to the j omega naught n. Doesn't matter. These are all constant frequencies. You follow me?
Mm-hmm. That makes sense. Thank you.
And that's important to realize. Whatever the way the signature there is of the frequency of the actual function, it'll be the same in the output, and it'll be scaled by the magnitude of the filter at that constant frequency and the phase of the filter added to the argument.
Thank you. That makes sense.
All right. Got it. I did it again. I blew the whole class. All right. Another question. Any other questions? We got about 2 minutes. It's better. I'm glad I worked through that. But can I get to where I'm going? Or do you have more questions? Ruth, you have more questions, or are you out of there already?
I'm good.
Anybody? I know people have class. That's why I'm in a hurry. Any other questions? All right. Let me tell you where I wanted to go today, but I didn't, which is not unusual for this class right now. But that's all right. Here's what I wanted to do. I wanted to go over here to windowing and talk to you about windowing. So I've got this PowerPoint, and the thing I'm really getting at, I'm going to do this longhand. That will get too confusing. I want you to pay attention to this. And this is why windowing is so important. You're wondering what it is for starters. Well, here's what it amounts to. I'm going to go to continuous time. You appreciate continuous time. Suppose I have p tau of t, and now we go back to the Fourier transform. That transforms as what? Tau times the sinc of omega tau over 2, right? You agree with me?
Mm-hmm.
What does this waveform look like? Let's call that p tau of omega, small omega. Well, that looks like this. If we just take magnitude of p tau of omega, it looks like this, basically. Right? I mean, that's a little high, but you can follow me, correct, class? Where's the first zero? Right there. The first zero is when this argument is equal to pi, isn't it? So right there corresponds to omega tau over 2 equal to pi. Remember, the sinc function is sine x over x. If x is omega tau over 2, the first zero is at 0 for sine. That's when x is 0. The second zero is at pi, right? Third zero is at 2 pi and so forth. That's the first zero. So the actual frequency would correspond to 2 pi over tau. That's what that frequency would be here if I'm graphing, right? All right, everybody with me? All right, where's the next maximum? The first maximum was at 0. Where's the next maximum? Think of a sine wave. It goes up, hits pi over 2 is a max, right?
3 pi over 2?
I mean, sorry, the sine, it would be 3. That's exactly right. So this maximum corresponds to omega tau over 2 be equal to 3 pi over 2. Do you all agree with that, class?
Yes.
So that means omega, and I'm shooting for a time crunch here, omega tau would be equal to 3 pi, right? Or
Right.
omega would be equal to 3 pi over 2, correct?
Mean over tau?
Over tau, right?
Oh, sorry. Sorry. Yeah, you with me?
Yes.
Yep.
Now, I want you to just think about this. Let's evaluate what this function's value is. First, I'm going to take p tau of 0. That's equal to simply tau. If you look at the sinc function, right? Right here, the sinc function, sinc of 0 is 1, correct? So when omega is 0, it's 1 times tau is tau. Now, what is p tau of 3 pi over tau? Well, what is that? That's going to be the sine of 3 pi over tau times tau over 2 divided by what? 3 pi over tau, correct?
Right.
All right, now look, what happens here? Take a look. You see
Tau's cancel?
the tau cancels there, and I get sine of 3 halves, or 3 halves pi, which has a magnitude of 1. It's actually minus 1. So this is minus 1.
Right.
What happens down here? Now I've got tau, and I have 3 pi, correct?
Mm-hmm.
Do you agree?
Right.
Yes.
All right. Well, that's basically going to have a value of this, isn't it, class?
Mm-hmm.
All right. Now, do me this favor. What is, maybe I can do it for you. I'm out of time. What I'm really going to tell you is that'll have in dB, it will be down 13.56 dB from the peak. So the difference between here and here in dB, and I'll do this next time, will be about 13.5 dB. And that is the actual frequency response of a pulse with no windowing. What you're going to see with windowing is this is going to go down to 40 dB below here, which is a factor of 10,000. This hump will be 10,000 less, but there will be a slight broadening, and that's with a Hamming window, and we'll cover that next time, okay? I try to answer your questions and get to my lecture material, but I felt it's more important to answer questions and go to new material. The old material isn't understood. We're going to do windowing on Monday, all right? What's the results of the poll?
Well, not everyone has voted, but 8 people have voted for next Wednesday and 7 people have voted for next Monday.
How about I do this, Lydia, I want you to work with the students on GroupMe and come back sometime today or tomorrow with a recommended test date for me, okay? I'll throw it in your hands. And any other, I mean, this is my office hour.
Okay.
You can
So
say,
just to verify for the homework, you're going to post it on Canvas for us to turn in by 5 o'clock this afternoon?
I'll put a homework 23, absolutely. That way, there'll be no uncertainty about where to put it in. And everybody should have an opportunity to at least put a homework into Canvas, even if it's not listed as 23. Can't you can put homework in there, right?
No, because we'll overwrite what we did for homework 21.
Oh,
Right. Yeah. So there has to be like a specific assignment assigned to turn it in.
hang on for 1 second. Tell me if maybe I can do it right now. Just stay there.
Is there any way we could put it into the files or?
I guess so. Let me tell you what, let me get on this right now. I thought I was on it, but apparently I'm not. I think I have to use this verification, but I'm not absolutely sure. Canvas. Wait a second. All right, let me get this. I'm in assignments right now, and I'm going to create a new assignment. Assignment name, how about just homework 23? And then this is where all right, points 10. Assignments. I think I just display grades as points. Online, text, and files. This is not everyone. Due date. Today is the 27th at wait a second. And then available until forever. All right, I got everything down there. I'm going to hit save and pub. Oh, wait, do I have to add sections? Assign to, and then. All right, and then I'm going to save and publish, save. Oh, sorry. All right, if you go to Canvas, tell me if you can see this as homework 23.
Yeah, I can see it now.
You guys, can you see it or not?
You can see it.
I can see it.
All right, if you got an assignment, try to upload it, see if there's any problems. I wish I was more familiar with Canvas, but years ago I used it and I didn't like it because it had a lot of problems, and so that's the reason I went to OneNote and took it completely outside the university, and I just let the students take care of the videos because they've got more interest in the videos than anybody, so they'll maintain them. Are you good with that? Did anybody try to upload one yet?
Yeah, I submitted one.
It worked?
It seems to have worked.
Give me 1 second. Well, this is my formal office hour. So, and I'm trying to get, a video office hour where we have more than one person. Makes a lot more sense than having an email stream that goes on forever about questions and answers with everybody. It's the same question usually. So more on questions about the homework. I'm not going to cover new material here.
We have a question about an upcoming homework that's due on Monday, the MATLAB.
Let me pull it out. All right, that's a fair thing.
Let's see.
Oh, you want the MATLAB problem? But let me.
It is, well, it's more about a formatting question, I guess.
All right, let me check out what that is. So here's the homework, go ahead.
So for problem 4, on that section, so question number like 4.1 or 4.2, do you want like the code to be completely copied and repasted over with the changes? Or do you want like a plot for every question, or?
You can, because it's so redundant, you're just going to change x of t 3 times, right?
Yes.
You got to change the sampling interval. So what I'd like is your base code, all right, and document it fairly well. And then when you change the sampling interval on these things, indicate it somewhere inside the legend or inside a title. I need to know what MATLAB plot is associated with what version of these changes, okay? Literally just copy 4.1 and literally put it into the legend or the title, put it into the title.
Okay.
And can you do me one other thing with this stuff? Could you put your name on the MATLAB codes?
Sure.
All right, and you know, the best way to do this, in my opinion, is if you go ahead and you have a Word document or the equivalent, and go ahead and get your code, cut it and paste it in there, then paste your figures in there. And I want to show you one thing with MATLAB figure, in case you don't know. If I get MATLAB, and let me just take the Hamming window here. We're going to go there and run this thing. See what comes up. Hopefully it runs. Now, this is the thing with windowing. I want to tell you one thing. You see this blue one here?
Mhm.
That's the frequency response of a pulse with no windowing. You see from here to here, this is in dB. The difference between here and here will be about 13.56 dB. You can't really tell on this scale, but it is. Now in dB, the next thing is with a Hamming window. Now take a look at this. It goes from here, and the next, this is called the next peak. The bandwidth really is associated with this part. But the next peak, it's called a side lobe, is down. Normally it's just down by 13.56 dB if we didn't do any windowing. With windowing, it's down 40 dB. And that's what you're seeing right here. And that's what we're covering. And windowing eliminates all these frequencies outside the range of interest. We really only care about this when we're doing radar work. We care about only the frequency at the only the frequency response at the transmitter. And we're going there. But here's my real reason for doing this. If you go to edit right here and you hit copy figure, this is the way you do it. Don't do a screenshot. Edit copy figure. Then if you pull it like even into here, if I wanted to do that, put it here and hit Control V, oh gosh, I hate it when they do that to me. Let me try to get a Word document. Give me 1 second. Now if I have a blank Word document and I hit Control V, it pastes it in its high res. It's called a vector graphics. When you get raster graphics and stuff, they'll blur. But here, if I go ahead and shrink that or enlarge it as large as I want, there is no definition loss. It doesn't smear. Do you see that?
Mm-hmm.
Oh, okay.
Make sure you use
Nice.
copy figure. And that would be like you'd put this in there, then you'd put your code below it or above it and indicate in the legend what figure it is. And then in your MATLAB, the way I'd like your homework to have your name like on the top here. So if I'm going through them, I might be able to do this without even printing it off. I can just have that and write down, you know, take my stylus, and I've got a tablet over there, and just grade them that way and get them back to you.
Okay. Also, another quick question. This was about the sampling. I knew that in the work that you said use DT as 1/20 seconds. I was just trying to figure out which part of the code was that, because I knew that one of them
Well,
is
that's the sampling rate, right?
sampling
So,
rate.
yeah, that's saying in between samples, there's 1/20th of a second. How about if I show you?
Okay.
All right. So if we Control C, and you know, Octave, I've been messing with. Octave works great. I've got MATLAB up, but Octave, if you're having trouble with MATLAB, just use Octave. It's fun. It's fantastic. So with MATLAB, let me open another window and just pull that down. Anybody here using Octave for their work?
I am, yeah.
Well, it'll be the same, but I always hit clear all, then close all, and CLC. There's probably one command that does that, but I don't know it. After that, I'm going to put down my variables. Now, I have one. I said TS, the sampling rate is 1/20, right? What
Yeah.
were some of the other things? Because I don't have that up on my screen.
The number of samples, I guess,
Hold on.
was, let's see. I can't pull up the homework while I'm recording.
It's all right. Number of samples is like what? 528 or 256?
256, I think.
That's fine. It can be arbitrary, right? What else? Anything else? Oh, the functional form, right? First, with this, what I'm going to do is if I have 256 samples, I'm going to create something. I'm going to say I is 1 to 256. Now what I've got is an indice. That's going to go from 1, 2, 3, 4, all the way out to 256. Then I'm going to create my time. T will be equal to, I'll call it T of I, will be equal to simply TS, right, times I. Now I've defined my time. With me?
Mhm.
After that, the next thing I do is define the value of the function without sampling. So x of t, tell me what it was, anyone? I don't remember.
E to the negative t u of t.
exp of minus t, is that it? People? Is that it?
I think for 4-1.
It doesn't matter. We could put any function down there, right?
Yes.
Agreed? Now, the only thing I've done is define this function. You'll notice I've defined I, I've defined t of I, and I've defined this. Automatically, because this is defined, this will be defined, and this will be defined. Interesting, these are going to be vectors that are 1 by 256, and you'll see it appear here when I run the program. Now, after that, the next thing I'm going to do is get the frequency equivalent, the omega equivalent. And I've showed you how to do this. Remember when we did DFT? All right. So I know that omega, and this will be sub I. I should create, actually I can say K equals I, and then we can use K. Now I'm going to say omega sub K is equal to, and here's the thing with the DFT. Now we have a finite number of points, not an infinite, doubly infinite number. We have a finite number. So we go ahead and take 2 times pi. That's, remember, the DTFT goes from minus pi to pi. Its range is 2 pi, right?
Mm-hmm.
But since we have a finite series, we have to divide it by n. Now these will be discrete frequency points. But that's still in the capital omega domain. If I want to compare it in the small omega, in the continuous frequency domain, what I have to do is take that and divide it by TS. So I take TS times that. Now I have the delta of omega that I can compare directly to a Fourier transform. Follow me? I hear a bird tweeting.
Oh, that's probably for me. I'm outside on my patio.
That's all right. But do you see what I've done there?
Yes.
Jeffrey, you asked about this, so I'm trying to make sure I'm commenting, right?
Okay, so could you explain to me why k is equal to I again?
I just chose an index C that would be associated with frequency domain. Remember, in the book, all their work with DFT, they talk about x of k being the value of the DFT at an index k. They're the same thing as I. I could put I there as well.
Okay.
It's the only reason. Now, once I have that, what am I going to do? Well, what's the Fourier transform for x of t? It's what? X of, and now you can put in k if you want, is what? It's equal to, this would be x, and I'll just put ft, that's the Fourier transform of that, is just what? 1 over what?
1 minus.
In this case, it would be 1 plus, wouldn't it?
Plus. Oh, right, because it's a negative t, right?
Right? 1
Yes.
plus j omega. And that omega here is going to be omega of k. Got me on that? Because that's the adjusted frequency.
That makes sense.
I hope this is still recording for everybody. Right? Now, and you can talk about this on GroupMe so everybody understands this. Now I'm going to go and work with the DFT. All right? So first I have to say that and I'll just call this x here. This is going to be the FFT of x. I'm going to do this whole thing for you. So that's the fast Fourier transform, but really it's the DFT. And I'll talk about the fast Fourier in a little bit. But now I take that. Now I'm going to get the shifted. Remember I showed you about FFT shift? Everybody?
Yeah.
No?
Yeah, I remember.
All right, so this is the shifted, but I'm just going to leave it as x. And it's going to be equal to FFT shift of XX. Now I've shifted it, right? I'm not done yet. Because when I plot this, I'm actually going to create a new frequency. And I'm just going to call it omega plot right here of k. And what that's going to be is equal to omega of k. But now I know I have to shift that by omega of n divided by 2, and then also minus just omega of 1. Now what that does, I'm going to use this frequency to plot. And now, I hope you can appreciate what I'm doing here. I'm going to try to show you how to get a direct comparison. Let me do this in stages. The very first thing I'm going to do is take a look at the Fourier transform of just x of t at the discrete time frequencies given by this. Are you ready to see this with me? You know what it's supposed to look like. So the only thing here I'm going to first put down is plot of, and this is going to be omega, comma, if I could only spell. Plot of omega, and the next value is going to be x ft. All right, let's see what that looks like. And I'm going to run this. I'm going to have to give it a title. It sounds like I got a problem.
I think you're missing
Oh,
a space.
No, this has to be in.
Yeah.
This has to just be
Yeah.
X. My bad. And line 11.
I think you missed the S's on
No,
your
I missed the I
N.
right here.
Mhm.
And
You haven't defined the variable N, you've only defined NS.
just do it this way. This is going to be N. My bad. Let's see if this works. Oh, forgot to do this. ABS. You want the absolute value of that, and then the phase. We'll do this in a second. Let's run this. All right, that's the Fourier transform. Do you agree? And if you want to go from minus omega to plus omega, you can as well, which we're going to talk about in a second. If I put omega p of k, or omega p here, and just ran that. Oops. That didn't work well. I can't do that with that. This has to be this way. All right. Now, I want to compare that to the DFT shifted. So first I'm going to just look at the DFT. Here I've got omega p, that's a shifted omega. And I think I went through how that's developed. First you have the DFT, and that goes from 0 to 2 pi. And what you need to do is shift all that information from minus pi to pi. And then once you do that, then you have to adjust the frequencies. Do you remember me doing this, by the way? Maybe
Vaguely, yes.
Yeah.
Why don't I do it bit by bit here? First, let's just take a look at the raw FFT. So I'm going to put XX here. So you can take a look at this. Whenever I hear vaguely, that means you don't really understand, but you remember it. All right, I'm just going to do this one. All right, that is the raw DFT or FFT. Understand? It doesn't make much sense to you. What you'd like to do is cut this in half and take this upper section and put it on the other side. That's what it should look like. So then we adjust it. So the next thing I do is I put X in here. Now this is going to be the adjusted one. And now you're going to see, it's centered. But it's not centered at a frequency of 0. It's centered at a frequency, it's about half the upper frequency. You with me?
Right.
So now what I end up doing is shifting everything. This is just the raw data to 256 points. But I shift it, and I do this, and now I'm going to put it in the frequency domain. So I put omega p here. And now, unless I'm making a terrible mistake, this should be comparable to the real Fourier transform. And there it is. Now, I want to tell you one other thing about this. Hmm?
So in this case, I noticed it's 1/2 of the n was where it was centered at, which would be 128. So
It's plus
essentially,
one, plus one. It's, I mean, minus one, because the zero, there's a zero frequency that's not counted. Did I just kicked off? Oh, there you are. I thought I thought everything fell through.
so in line 15, that's essentially where you're shifting it by half of your n value, right?
You're just shifting the frequencies. Now, this, I'm going to do one thing right here, all right? I'm going to do the direct comparison that you're going to do. This is a way to look at an FFT of anything, I mean, a Fourier transform of anything, and think about it as if it was a continuous time Fourier transform. Follow?
Okay.
Now, if you sample fast enough, here's the thing that you're going to do. Forget this right here. Well, wait. We're going to leave, I'm going to go ahead and comment those two. And now I'm going to show you what happens here. This is the actual FFT right there, right?
Yes.
All right, now remember what I said for comparison's sakes, what do? I think I'm going to go back to the doc cam for 1 second, because this is kind of important. When you do the comparison, you said your actual Fourier transform that you had, so that would in our case be 1/1 plus j omega, right? You let this omega be the frequencies that are discrete. So this is going to be 2 pi over n divided by ts times k. These will be at distinct values of k. And that's equal to, now here's what we do. This is the Fourier transform, continuous time Fourier transform. We're going to say this should compare exactly to this. If I have 1 minus e to the minus j, and then the omega here is 2 pi over nts times k times ts, and the ts's will cancel. We divide that by j times 2 pi over nts times k here, and then we multiply that by the actual x, which is the DFT, we call it x of k. And you can do the comparison. Now I did this for you, right? I did that in the code that I gave you. Do you remember that?
Right.
Okay, I gave that to you, but I'm going to show you how this works right now. So if I take this code right here, now I want to adjust this. So I'm going to call it x adjusted. Will be equal to, watch this, it's going to be 1 minus exp, right, to the minus 1j times my omega, which is in line 11, times ts, and I'm going to have to put a dot in front of there. Then close that parentheses, dot divided by 1j times omega, all right, and that's the omega on line 11. Close that, and then times x, xx. Now, what that is, it's adjusting the actual DFT, or FFT in this case, so we can do a comparison, direct comparison. Now, when I do this, let me take the raw frequency out first. If I just plot this, okay, where's the error?
Should it be omega of k?
Shouldn't matter.
Okay.
It shouldn't matter. Let's just hold on a second. This is dot times right there, I think. Try that.
Maybe the dot XX.
Oh,
Wait.
you're right. You're right. And one other thing I'm going to show you should do is something I didn't do. That.
Also,
And they, huh?
quick question. So what if you bump up the number of samples from like 256 to like 500 and something? Would that increase the accuracy or
The resolution? Matter of fact, let me go ahead and show you. That's what you're going to discover when you do this. And I'll show you parts of this. The thing I wanted to do is a comparison. So first I'm going to put it versus the actual frequency, and that's the omega. All right, now you've got the actual frequency. The next thing I want to compare it. So what I'm going to do is this. And now I want ABS, the XF of t. Now that's the actual Fourier transform just being evaluated at specific frequencies, right?
Okay.
All right, take a look at this. Much of a difference? Virtually identical,
Not much,
right?
yeah.
All right, now the one condition for this to work is, you see we're sampling at 1/20 the second of this function, e to the minus t, right? Take a look at the difference. If I have e to the 0, exp to the 0, that's 1, right? exp to the minus 1/20, oops, over 20, that's virtually the same. It's within 4 or 5%, right?
yes.
Right.
All right. That's what's critical. If this isn't the case, then it won't work. By the way, when you get about the zero crossing, when you're with, if you have a function that's oscillating, when it starts going through 0, all of a sudden the value just above 0 and just below 0 are quite different. One's negative, one's positive. Do you follow me? That's
Right.
when this thing breaks down, but it still is only at a very small number of points. So overall, if you sample it, it'll still compare very well with you. Now, you asked me something. What happens if you make this bigger? And I'm going to have that just going out to n.
Is that why you don't start I at 0 or?
Well, the MATLAB indices will not allow that. If I
Okay.
use I as an indice here, it has to start at 1.
Okay.
You can try. You can play with this. I'll tell you, there's ways I do it that are a little differently, but I want you should be able to see every single bit of this code, why it works. There should be nothing that you're wondering about. All right. But when we come here, as you said, well, what if we have too much more, much less? Let's just go down to say 16 points and see what happens. What do you think is going to happen?
It's not going to be very accurate.
The agreement will be poor at best.
Yes.
And as you might have guessed, it's pretty crappy. All right. All right. What if I make it much, say we go to 64. Now I got 64 frequency points. It's getting there. What if I make it 1024? Any guesses?
Should be really accurate at that point. If 256 was really close.
They're just about on top of each other. All right, just about on top of each other. You'll notice though, the range here. Let me do this. What was that one again? Oh, it erased.
It's 128 is what it looked like.
All right, you see where that is? It's right about here, right?
Right.
And I'll tell you why it doesn't change in a second.
Yeah. Still
Because-
stops at 128.
Because take a look at this. What am I doing? For this frequency, I take 2 pi over TS. That's the fundamental in capital omega. I divide it by n. That's the length, right? And then I multiply it by I, but I goes from 1 to n. So the upper frequency is capped by TS. Really 2 pi over TS is the cap on that. And if you wanted to put it not in the omega domain, suppose you wanted to graph it versus f, what would you do? You would just take this by 2 pi, right? This is not an efficient way to do it, but if I divided that by 2 times pi, and then I divided this by 2 times pi, isn't that effectively putting it versus frequency in hertz, not in radians per second? Correct?
Yes. Mm-hmm.
All right, you see it goes right out to 20 hertz. Now, here's something. Suppose I take this and instead of just having an exponential, suppose I multiply it by a cosine of, say, wait a second. We're going to have to sample this faster. I'm going to make my sampling I'm going to make it 1 over 100 seconds. And suppose I have a cosine of 20 times t. What do you expect to see? Wouldn't you expect to see something that's a strong signal presence at 20 hertz? Or, oh, this would be, why don't we do it this way? 20 times 2 times pi, because that would be f. F would be 20 there, right?
Right.
Yes.
You all see it?
Yes.
Yeah.
All right, let's take a look at this. And this e to the minus t is going to smear that a bit. It'll broaden it, but let's see what happens. All right, well, I didn't change the whatchamacallit, the actual Fourier transform right here. So you're going to have to forgive me, but we'd have to adjust that for comparison. But you see, we're going to strong frequency presence right there. By the way, this is sort of an artifact that I'll have to talk about later. But you see how it's right at 20 hertz?
Yes.
Right.
And we've got a decaying exponential too, but this is just the positive frequencies. If I got rid of that exponential altogether, it should be a bit narrower. Yeah, you see how it's just a spike? Now in radar work, when we do fast Fourier transforms, and we basically look at them adjusted so it's versus hertz, this is the kind of signatures we're looking for. But what really happens is we're pulling them out of the noise because there's a noise floor that there'll be all sorts of jitter around here where you see stuff. And that's why windowing becomes so important, because when we use a window or we use what's called a finite impulse response filter, we can get rid of all the noise around this and just look at the frequency where there should be a signal to see if there is. And I'm going to get to that in upcoming lectures. But that should have answered your questions about the comparison.
Yes. Also, Dr. Baginski, I knew that you said a few days ago that you wanted the test to be for we would open up like the submission window for like 2 hours.
Yeah.
Then turn it in at the end of that time. So for the people who have class afterwards, this class,
how about we start the test an hour early?
there's
yeah.
people who have class before. I have class before that.
Yeah,
Lots of
I have
people
class
do.
as well.
Lots
I
of us
didn't
have
know if like
Datacron.
in the afternoon is better,
Why
like
don't we just do
three in the afternoon or something, where people
Lydia,
might not have something.
Can you guys just get on group me and see if I make it for a, oh gosh.
I could ask for does any of y'all have like a good window for a 2-hour period where y'all are free instead of having on a specific day?
You know what?
Possibly.
I don't want to put it on the weekends though.
Right.
Here's what I'm thinking. We don't have to have this test during class time, right? So is there any afternoons when you got a 2-hour window?
Like my Thursdays are completely free.
Why don't you, can you get like a Google, what do they call it, Doodle pad or something? And just,
So
can you guys?
yeah, I didn't know if that was possible. Something like a Wednesday or Friday, whenever anybody wanted to have it, maybe at like
this would be
3 to 5 in the afternoon instead.
Can you get, Lydia, can you go ahead and find out a window when everybody can take it and get about 2 hours? Okay.
It might be a little bit hard for scheduling because there's 26 of us. So
this should, what I'm thinking is this. I just bet you that most of you are pretty similar in your class where you are academically. You're about taking the same classes, right?
Right. Yeah, there's multiple people in multiple of my classes.
Your labs in the afternoon are the things that are staggered that are a problem, right?
Yeah.
Yes.
Like Lydia said, her Thursdays are open, but mine, that's when actually my signals lab is in Thursday afternoon.
Well, what if I make it a 3-hour window from like, I make it from 10 till 1? Wouldn't that cover everybody?
That should probably cover everyone, but I'm sure that there is at least one person
It's
who
like,
who would
The
have
only
a.
thing I could think of is like with Ruth having her class after here,
yeah,
then she'd like take the test for an hour, have to like take a break and go to class and then
yeah.
Why
Like,
don't we do this? Well,
get back on the test.
how
I
about
think
we,
that I think a 3-hour afternoon in the window in the afternoon would probably work for everybody. Even like even me with a lab, like with a 3-hour window, I would still be able to
I'm just
work
thinking,
in the test.
I mean, I don't like doing this. I know over in business, they give night exams and stuff. I'm not a fan of asking people to work outside of the 8 to 5 window because other people have jobs. I've got quite a few people in this class. No, I've got at least 2 people, I think, in this class and one of my other ones that are full-time employed.
Right.
And so asking to do something outside of the 8 to 5 zone is a real tough thing. Let me think about this a bit. I think if we do one where we put
Maybe like 2 to 5 on a Wednesday or something.
No, but other people are going to have labs. And that's a real bad time.
On Wednesday.
But any afternoon between 2 and 5, there's labs going on in signals and systems and other courses.
Oh, that's true. I didn't think about Digitron as well.
And but if I do this, now go with me on this one. All right, if we start at like 10 of 10, all right, and then we go, so that would be a total of 1 hour and 20 minutes between that and the next class official starting time, right? We have
Right.
a 10-hour window between a 10-hour, I'd say, adjournment between courses, between one ending and the another starting, right?
Yeah, there's 10-minute interval.
All right, so if we started exactly at 10 of 10 on the test date, and then we adjourned, let's say an hour and, not an hour and 20, make an hour and 25 minutes later, and I'll make the test suitable for like 50 minutes, so you'll have that cushion to take pictures and get it up and work around technical difficulties, all right? Is that fair? I'm not going to make this a terrible test. What I'm going to do is this. If we start it at 10 minutes before, I send an email out, everybody gets it, right? Now,
Right.
however you want to work it, if you want to print it out, fine. If you want to take a picture of it, fine. If you want to use it and just have a stylus on your tablet and write on that, that's fine too. However you want to do it, you do it. But we'll run through a test on this, like say the day before the test, all right?
Okay.
Then we do a dry run, see if there's any problems. You're going to get we'll start 10 minutes early and we'll go 15 minutes after. So that's basically going to be 1 hour and 15 minutes instead of a 15 minutes, right? That's 25 minutes longer.
Right.
Are you with me? That should cover it. I can make a test and tailor it for you to work it in about 40 minutes. And with all the other technical issues, that should be plenty of cushion. What I'm going to do is hopefully prevent people from trying to Google everything and all that crap.
Yeah.
Because I'm going to make it up specifically with that in mind. I'm going to try to eliminate the possibility of going out there and finding an answer quickly. You'll have to work through it.
I mean, I think that would work as well.
Are you okay with that, Lydia? And Nick?
So you would limit it to the time and make it so you only have to do it in 45 minutes, or like expanding it to a 3-hour window?
No. Here's what I'm
It'd be
planning.
it'd be an hour and 15-minute window, but like a 40-minute worth of test.
You'll have like and I do this, I know about how to gauge how long problems take. So I'm going to gauge it for about 45 minutes worth of test material. There may be a MATLAB thing or an Octave thing that I have you do. I haven't decided on that.
Oh, no, please no.
Please,
That
would,
sounds
would not be good. Like writing code by hand is not fun at all.
All right. I hear you. I'm going to have something that is doable in 45 minutes by a a standard person who's been keeping up to date with this stuff. There will be a lot of things there's no way you can get at.
Okay. So like if
but
oh, sorry.
What I'd like you to do when you're doing the exam, see, I can't, it's an honor system. I can't check your phones or anything, but I'm asking you to do it on your own. Maybe I'll put a signature line for, I did not in any way collaborate with someone on the exam. There'll be people that aren't ethical, and it doesn't matter what I say, they won't do it. But I'm just asking you to show your own work and don't do something underhanded. And I think that is doable. But if you take a look at the problems, somebody's always got, well, what kind of problem would he ask? Well, homework's a good time. Hey,
Dr. Baginski, quick question. So for this kind of questions, I knew that you said that it would be a little bit, before you say it's a little bit of a harder difficulty, but you gave us more time to turn it in.
Well, I'm
Would
not
this be
going to have this. Yeah, let me give you an example problem. All right.
Okay.
Let's think about Fourier transforms, and let me just do this on this camera, because this is the best way to get rid of it. So I'm on my camera now, am I not? And I like this doc cam. I hope you guys liked it better than the.
Oh, this has been the best lecture so far since we started back. Like, honestly, this has been really, really great for me, at least.
Yeah, I agree.
So.
All right, suppose I ask you this, a typical question for me, right? I'm going to ask you to convolve two signals. One signal looks like this. Call that x of t. And the other signal looks like this. That's h of t. Show me how to convolve them and do it. You're going to have to show me the steps exactly. So first is you pick which one you don't want to flip and shift. Well, it doesn't really matter. I'm going to leave that one alone. So I'm just going to put it there. This is my x of tau, right? And it looks like this. That's 1. This is tau, correct?
Yes.
Now
Okay.
I flip this one. And when I flip this one, it looks the same, right? This is a t, this would be at t equals 0. Remember, this is a tau domain. Now when I shift it down to -2, right? Now this would be for t equals -2. And remember, in the original one, this was this point here. Sorry, this was 2, and this was -2, right?
Right.
Now when I start shifting, what do? You're going to add t to that and t to that, correct? The upper and lower bounds, you add t when you shift it. Now we say for t equal -2, the lower bound would be -4, and the upper bound would be 0. You all see that?
Yeah.
Right.
Mm-hmm.
Now you let it go through here. So as the window goes through, it starts going over that. And you're going to get values. When you talk about the convolution of x convolved with h being y, you're going to say for y, right here for t less than -4, it's 0. Then y between t equals -4, or -2, pardon me, -2. For t between greater than -2, right here. Now it's starting to actually, you can see at -2 it starts, and from there to 1, from -2 to -1, the value is just going to be the integral of that, right? And that's going to be, if that is a, it would be at squared over 2, right?
Mm-hmm.
Right.
All right, then keep letting it go. Now look, as this thing's moving through, the width of that's 4. So when you go to at -1, all of a sudden it starts coming out. Now this entire thing is immersed in this pulse, right?
Right.
It's going to be a constant, and the value of that's going to be just the area here, which is a over 2. So then it's going to be y equals a over 2 from t greater than, that would be -1 till what?
And that is,
Right? Because the window is actually about that big, right? So from, that's -1, -2, -3, right?
Mhm.
So from there to really 3. No, not
Yeah.
3. 2.
It should be 2.
2.
Yeah.
2?
2, yeah.
Mhm.
Then after that, it's going to
Yeah,
come
that's
out.
right.
It comes out. And you know what? It'll look just like this, only time reversed. And the plot would look like this. It's going to be at minus 2 is when it starts, right? And it would do this. It's going to be like this. It goes up, -1 here, flat. That's 1. Out to 2, right? And then it'll just,
Yep.
and that's what it'll look like. But that kind of a problem, and that's a fair problem that requires some thought, and it's very hard to get that off the internet. Now people come up with things, well, I'll draw it, stuff like that on that Java app that I gave you guys. Yeah, you probably can get away with it, but try to write it down mathematically. So if you know,
So there, like, would you want us to keep going with the y values for
it's
like
only
t greater
non-zero.
than 2?
No, it's no, from t, yeah, sure, for t greater than 2, less than what, 3. It's going to have a value. That's this part right here, right?
Right.
And then for
Or,
t, it's 0 else.
and then 0 for anything greater than 3.
Mhm.
Okay.
That's a fair problem. But that's a more difficult problem than some other ones.
Just real quick, probably a dumb question, I guess. For that fourth value there, can you explain what that would be?
This,
I know it's kind of like, yeah, the inverse almost of,
the only thing
you know,
you're doing
where,
is what? Now your integration starts here, which is going to be t -4, and it goes to 1, right? And the integration is what? It's just tau times a d tau, isn't it? You're basically going to integrate from from t -4 to 1, right? And the function is what? A times tau d tau.
right.
And that is what the value is between 2 and 3. This would be for 2 greater than t less than 3.
Why wouldn't it be t minus 2, because isn't t the center of our rectangle, the way that we've defined our bounds? Because we start
You're
at,
right, you're right, you're right.
okay, okay.
Sorry.
And then the only other thing is
Because when
that
it's 2, this is 0, look. 2
Mhm.
minus 2 is 0, you're right.
the only other thing is that the pulse is at a height of 2, and I don't think that's been included
You can put
in our,
that down here, you're right.
okay.
You can actually weigh either that right there or that.
Yeah.
Okay,
And
Yeah.
that.
just to make sure the video is correct.
Yeah,
That's my
thank
main
you.
concern.
That's right. I should have
Yeah.
made that 1 because I'm trying to work through
So
this.
you're just multiplying by the magnitude, right?
Mhm.
Makes sense. Okay.
So that's a test level kind of question
Yeah,
for the
sure.
convolution,
Yeah, but
you'd say?
sure, and I could have maybe 2 triangles convolve those, or an exponential and a triangle, something like that.
Sure.
If you know what you're doing, you'll know how to do it, and if you don't know what you're doing, it'll be clear.
Okay.
Baginski, could we expect something like a sine or a cosine
Sure.
be convolved
That's fair.
with each other?
Those are very fair questions. Yeah. Any normal function, because convolving a cosine or a sine is fairly easy. You're not going to shift that one. You're going to leave it as cosine of omega naught tau or whatever it is, right? And then you're going to shift the other thing. And if it's the square block, really, you're just integrating a cosine between one point and another in the window.
My biggest concern with those is like graphing them afterwards, because like I can perform the integration for it. It's just I don't know exactly how to plot it afterwards.
Well, let me tell you this. If you go ahead and integrate a cosine, suppose we just, for the sake of it, we're talking about, we've got x of t is equal to cosine of omega naught t. All right, and this is for t greater than 0, say less than 5. Just say that. And we're going to have h of t equal to a pulse function with tau. And let's shift it from t minus tau over 2. So this is a window that's shifted to the right, so it's all for positive values of t. It starts at 0, it shuts off at tau. All right. Now, if you're going to convolve those two, which ones, if you want to draw them, and you should draw them, I'm not going to mess with shifting that one at all. And I can take a look at a cosine. If this is tau, it's going to look something like this. Cosine of 0 is 1. It starts like this, and it's doing this, right? And this is simply trying to show you cosine of omega naught tau. Now, and of course, it goes on like this. My window that the actual pulse function right here, my h of t looks like this, h of tau, and that's not shifted, right? That's what, if just plot this versus tau, isn't that just a pulse function?
Yep.
Can you see it?
Yes.
Just look at that. That would be a pulse function. That's tau. That would be 0. And this is, I mean, sorry. I'm using tau there. How about I make that k?
Okay.
And make that k. That way, this will be k. It's another symbol. Now, if you flip and shift that when I flip it, it looks like this, right? Height of that's 1. Right at 0 is when the overlap starts, correct?
Right.
Now, if this was going forever, actually,
You can incorporate a U of
let
t.
me do this. Put a u of t there, so we won't get into crazy possibilities. But if you just take a look at that, right? Now what happens? Well, even if it went on forever, you would literally start. This point is going to be what? This is t minus k, and this is still 0, correct? So it is, this is going to be t. At 0, t equals 0. This is versus tau, right? That's 0. That's minus k. If the thing went on forever, cosine waveform, minus k to this point, which is going to be 0, right? I mean, it'd be t, correct, class?
Yes.
If this cosine went on forever, all right, what is your integral going to look like?
From minus
T
infinity.
minus k to t, correct?
Oh, right, because you're going
No.
in the window from t minus k to t. Okay.
Yeah, right. So it's
That's
going to be the
right.
integral of exactly cosine of omega naught tau d tau, and it starts at t minus k and it goes all the way to t. Now that integral is what? Well, that's 1 over omega. Integral of a cosine
Sine.
is sine, right? It's a positive sine, right? Of omega naught evaluated at the first limit t minus sine of omega naught at the lower limit, t minus k, correct?
Right.
And that would be the convolution
Yes, sir.
for an infinite cosine waveform. Now, you can do a trick here. Remember, sine A plus sine B equals, you could do a half angle thing if you want, but this is a perfectly acceptable answer.
Okay, so what would be the graph of that? If
Well, the problem is you got to tell me over what time frame. If you start at 0, what is it? At 0, this is 0, correct? And this is just the sine of minus k.
okay.
That's what it'd be. But I tell you, I wouldn't push too much in a graph on this one.
Okay.
This the thing is, you would break this, the way I would do it if I had to do this, I'd use a half angle formula on this. And then I would combine the sine of omega naught t and see what the coefficient is left there, and I'd graph that.
Okay. So like if you had an exponential convolved with, let's say, like a sine wave after 0.
So e to the minus at u of t, you talking about?
Yes, sir.
I'm convolved with a sine of
omega t u of t.
omega naught t, right there?
Yes, sir.
Okay, we can do that one fairly easy. We know what a sine looks like, right? But it exists for forever, right?
Yep.
All right, this is a decaying exponential, right?
Yes, sir.
Right.
When you flip it, it'll look like this, right?
Right.
Then when you shift it, it'll start looking like this. So you're going to start at minus infinity and you're going to go to t with the integration.
Okay.
All right, now that's a tougher one because that's an exponential times a sine wave. And that integration is a little more difficult, isn't it?
Yes, sir.
That integration, the way I would do it, I take the sine of omega t and use Euler's on it, and break it down to e to the j omega naught t minus e to the minus j omega naught t. Or yeah, e to the j omega naught t minus e to the minus j omega naught t over 2j. And then I'd combine the exponential terms and do an integration each of those and then evaluate it. But that's a more difficult integration.
Okay.
Okay. I think I've got to head out, guys, but I appreciate all the extra help, Dr. Baginski.
Yeah, hey, pass the word that there's always going to be an office hour right after this class for everybody. Because if I'm answering questions here, I won't have to answer the same question 100 times.
Right.
Because
I think there's a lot of people that watch the YouTubes that Lydia posts afterwards to catch up on office hours, that people that weren't able to stay or have other classes or whatever.
I don't know how many people have other classes, but you know, I'll try to make myself available. If you want an office hour later, just let me know if there's a significant number of people, and I'll be happy to do one for you. Because this whole,
all right, sounds great.
I got to say this: the provost has been very, very supportive of being as flexible as possible. If I want to hold a class on Saturday to try to help people, you know, it's more work for me, but if you can help the students get up on speed, because some of you, it really helps me. Most of the graduate students I've had in over my lifetime, and a lot of people are, they're handpicked from the undergraduates that are taught, that I teach or they teach. And this is the single most important class for all my research for these guys to know. I can help you with radar and EMAG. I can't reteach this course to a student that's going to be a grad student. And if you're good here, if you're sharp in this course, you're probably going to do exceptionally well in graduate school in terms of the course material. But this is a challenging course. Don't kid yourself. This will challenge you more than probably any other course.
I'm not kidding myself there. I know exactly how hard it is.
Well, when you get into, we're gonna go through Z-trans. Actually, I'm doing windowing on Monday, and I will do windowing. It's the last thing I do, windowing, and then I'm going to show you how to do FIR filters too, from first principles. But I want to take care of that on Monday, the windowing for sure, and give you examples. And then I'll do FIR filters. That's finite impulse response, and we'll do infinite impulse response filters too. And you'll see the differences and the benefits. I'll tell you this much though, this right here, like, a student of mine, grad student and myself, just submitted a paper that involved encryption codes used for radar processing and getting rid of problems that are called ambiguity problems. And his strength is this. I mean, that's one thing I appreciate. He's extremely good at all the theories behind the DFT, the FFT, continuous time Fourier transforms, DFTs. You're going to see Z transforms and how to actually design systems based on that. And if at first you hate this stuff, realize you will probably appreciate it in the future if you're working in any type of signal processing area, which everybody is going to end up in some way. Okay. Anything else?
I think that's all for me. Oh, go ahead.
This is more of like if you could work it, or it's another semi-convolution related question.
Go ahead.
About like ln of a function, I guess.
Log. All right.
Log.
Give me the function.
Let's say like a pulse convolved with like a logarithm.
Convolved with the log of t.
Yes,
Is that
sir.
what you want? Okay. You know, log of t has something odd happen. What's the log of 0? Minus infinity, right?
Okay.
Log of 1 is 0, but if this is t, log of 1 is 0, this is minus infinity. This is one of those things to convolve this thing. What do you need to do? You need some way of establishing this thing be non-infinite. So you'd put what? A u of t minus some, call it a value. So it's going to start not at a negative infinity.
Okay, so you're giving it like a distinct starting point.
Yeah, you're doing this.
Okay.
Now when you convolve that, it's not too bad, because now you can see that what? If I have, I'm not going to shift that. So if this is tau, here it starts at some value of A, and it looks like that. Log of tau, right?
Okay.
Now, your pulse originally starts at 2 tau over. And you know, let's not use tau. Let me use K. Right?
Okay.
And this is which is tau. Now you can see when K over 2, see right there, there might be overlap. You have to see that if A is like, say 1/2, and if K is, 1, then it would start right at the instant at t equals 0, wouldn't it?
Right. Starts
this-
at K equals 1.
Yeah, this would be T, and this is really going to be K over 1/2. So if K is equal to 1, it would exactly start at t equals 0, and there would be no overlap before that. But after that, all the way up to what? K, it's just integrating the natural log. What's the integral of a natural log?
Oh boy.
Excellent question.
What is the integral of 1 over x? Natural log, right?
Oh, so no.
No, you can't do it that way, Lydia. You'd have to integrate the natural log, right? And then you would have to evaluate it between the lower limit, which would be A, and the upper limits, which would be A plus K. Or I'm sorry, it would be
T plus K.
K over 2 plus T.
Okay.
Then once you go through there, right? Once you go through there, then you're integrating from the lower limit to the upper limit all the way out to infinity. Okay?
Okay. Okay.
Yeah.
That makes sense.
Yeah.
All right.
I guess once it hits a certain point, then it would just be completely overlapped with
It starts being
the
more and more
log
of a
function, right?
constant, but it's going to grow to an infinite value because the log of infinity is still infinity. Isn't it?
Right.
By the way, what is the integral of log x? I'll show you how I'm going to do it. Let me new share. I'm going to share that screen. Actually, I don't have to share that screen. Do I? I just shut this down. The only thing I have to do is shut my camera down. You are looking at that, right? Now do you see the screen, the MATLAB screen?
Yes.
Yes.
All right. Well, if you want to do a symbolic integration, I'll leave that there. But and then I'm going to put int. I think that's integrate. Let me just see if this does that or not. Yeah, it did it. So then if I integrate, oh, it's log in MATLAB. Log of x is natural log of x. Let's see what that is. X times log of x minus 1. And the integral of log base 10 of x is going to be similar. Okay. Y'all see it?
Yeah.
All right. Symbolics are great. If you're using Octave, you have to download a package to do symbolic integration, by the way. It's not hard. It's easy to do, trust me.
Any idea where like those packages are? Can
Sure,
I just Google it?
Just type in, go into your window and either use Bing or Google and just type symbolic, just symbolic Octave download and you'll find it.
Symbolic Octave download.
And it'll go to one of these sites that are GNU sites and you'll be able to download it easy. All right, am I free to go?
One
believe
last
so.
question about this is more of like a class question. So
Go ahead.
from the group me. So this is, do you still plan on testing the material that you outlined earlier this week? like the one convolution of Fourier series transform.
That's it.
So also, do we need to have another poll to ask for different test days, or do we want to still continue like the Monday, Wednesday, or Friday during the current test time, with it being 45 minutes?
Find out what they say, and then what I just explained to them, everybody, that I'd like to start the test 10 minutes early, and then end the test 15 minutes early. I'll send out the test probably at least 15 minutes ahead of time. So I'm going to give you a heads up to print it out or whatever you need to do to get ready to go.
Okay.
And now I'm anticipating, and we'll do a dry run on Monday. How's that? Just something simple, so I can send something out, you work it, and then upload it, and see how it works. Okay.
Okay.
Uh-oh, I got a meeting at 12. I'm missing my.
Thank you. I really appreciate it.
Yeah,
All right.
I gotta
Yeah,
go.
definitely. I appreciate
you.
all the help. Thank you
Sure.
very much.
Not a problem. I gotta go. I got another meeting. Oh, yeah.
Bye.
Bye-bye, man. How do I get out of this meeting?